All right, welcome back, everybody. I hope you all enjoyed your break. Today, I'm going to slow things down a bit. We had kind of interruption to the class, and I want to make sure the material from last time is reinforced. In particular, I want to make sure you have everything that you need for your homework. So I'm going to slow things down. Today is going to be a little bit boring and procedural because I want to make sure you know exactly what you need to do on homework 3. And because we're going to be on a little bit compressed timeline from now on, we are not going to be able to cover all the material in the class. So I'm going to have to make some changes to the curriculum. But today we're going to be going through just some different procedures for solving LTI systems in the frequency domain. Okay. Are there any questions on course logistics? Anything else before I move on? Okay, so last time we talked about Laplace transforms. We talked about what they are. We talked about their properties. And effectively, we showed that a Laplace transform is a change of basis that takes us from the time domain, which is we described as the domain of Dirac deltas, to the frequency domain, which is the domain of complex exponentials. Okay, and we gave the form for the Laplace transform, specifically the unilateral Laplace transform, which is given by the following integral. And we showed how Laplace transforms, primarily for this class, they're going to be useful for solving particular solutions to differential equations. In the first part of this course, it'll be for single variable systems, but later on, we'll generalize this for systems of LTI differential equations. So we showed how they can be useful for solving the particular solution that corresponds to some given input. We'll also show how looking at systems in the frequency domain can help us analyze their fundamental properties a little bit later on, specifically their stability properties within the next couple of lectures. But for this class, at least for now, Laplace transform is going to be useful for solving LTI systems more easily. So we showed in previous lectures that we can find the general solution to an LTI system. So we can find the response to some arbitrary input by convolving the input to the system with what? Does anyone remember what it's called? So we find the response to a input by convolving the input with what function? Impulse response function. Great. And what is the impulse response function in your own words? I want to jog your memory a little bit because we haven't met for a while. What is the impulse response function? Just in your own words.
The response that you would get for a particular Dirac delta function or a particular impulse.
Right. So it's the response of the system to an instantaneous impulse as represented by a Dirac delta. Very good. So it's kind of it characterizes the response of the system to that impulsive input. And then by treating our general input to the system as a train of Dirac deltas, we can compute the overall response to any input. So we showed that we can solve LTI systems more easily by replacing convolution, which is kind of convoluted. It's given by this integral here. We can replace convolution with simple multiplication. Specifically, we can take our input, we apply the Laplace transform to produce the input as expressed in the frequency domain. We apply the Laplace transform to the impulse response to get the transfer function, which we'll talk a little bit about today. And then we can simply multiply the input and the transfer function in the frequency domain to get the response of the system in the frequency domain. From there, all we need to do is apply the inverse Laplace transform to get us back into the time domain, and we have our solution to any arbitrary input to our LTI system. Okay, so that is one of the main selling points of the Laplace transform and working in the frequency domain in this class. It's going to be really useful when we talk about control later on, particularly for finding the control inputs that'll get us the response we want. Okay, so to recap, this variable we called HS, this is the transfer function of the system. So what is the transfer function? Just to jog your memory. What is the transfer function?
You do the Laplace on the left-hand side of the derivatives, then you factor everything out, so it's all frequency coefficient.
Yeah. So there's kind of a simple one sentence answer that might help you think about it a bit. So the transfer function is the impulse response function in the frequency domain. So that's another way you can think of the transfer function system. We're going to be using transfer functions for a while coming up, but you could think of it as the impulse response in the frequency domain. Or in other words, it's what you get if you take the Laplace transform of the impulse response. Okay. And as I showed on the last slide, you can obtain the particular solution to any LTI system just by multiplying that transfer function with our input. We'll go through some examples of that today. Now, we ended last lecture by looking at how we can take the inverse Laplace transform more easily to get the solution in the time domain. So the transfer function of an LTI system can be written as a rational polynomial in S, where S is our, the input, not the input, the argument to our function in the frequency domain, representing our kind of complex variable. So our transfer function can be written as a rational polynomial in S. It can be factored into its zeros on the numerator and its poles on the denominator. So in the next lecture, we'll talk about where these names come from. But if you have a polynomial, you can factor it into a product of the zeros on the numerator and the poles on the denominator. And we show that this type of system is generally easier to solve through what is called partial fraction expansion. Okay, so today what I'm going to do is I'm going to give you the techniques that you're going to need for homework 3 in particular. We're going to slow things down a little bit. We're going to look at using partial fractional expansion for solving LTI systems for both distinct and repeated roots. Okay, and we're going to look at using the Laplace transform to solve higher order systems. So previously, we've only looked at using the Laplace transform to solve first order systems. Today, we're going to look at higher order systems. So as I mentioned, today is going to be largely procedural because I want to make sure you have all the solution procedures you need for your homework. We're going to deal with a bit more conceptual material when we come back on Thursday. Okay. Are there any questions on any of the concepts that I have recapped so far?
I had just one question. In the frequency domain, the variable S, is it just a variable? Because I think in the course packet is, I think somewhere it is shown that S is equal to sigma plus JW. So what did that mean actually? Sigma and W, omega, sorry. Omega.
So it's a complex valued variable, right? So time is generally just in the real numbers, right? But your variable S is going to be complex. So you can think of it as lying in a 2D plane with a real component and an imaginary component.
Oh, okay. But then does the sigma and omega, does it specify anything in particular, or are they just two random variables?
I just meant those two variables to specify kind of the magnitudes of the real and imaginary component respectively.
Okay.
Yeah.
Thank you.
Right. Good question. Thank you. So yes, in the frequency domain, we're generally dealing with the entire complex plane as opposed to a real number line. Very good question. All right. So let's recap. Let's look at using partial fraction expansion to solve LTI systems. And first, we're going to look at the case of distinct roots. Okay, so last time I showed you, we have that we can factor some function in the complex domain. So in this case, our transfer function doesn't necessarily need to be the transfer function. It can be, for instance, we could have fs, which could be equal to hs times us. But it can be factored into essentially a linear combination of terms with the poles in the denominator and a set of scaling factors in the numerator. So something like this, and this is an equal sign right here. So we can take any rational polynomial and break it down into a linear combination with the roots of the denominator in these denominator terms. This is just a mathematical fact that we are going to use. So to determine each one of these coefficients, C1 through Cn, we can multiply through. So let's just take the first denominator here and multiply it through. We'll end up with s minus p1 times big F of s is equal to C1 s minus p1 over s minus p1 plus C2 s minus p1 over s minus p2 plus dot 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 plus Cn s minus p1 s minus pn. Okay, and we can take this expression and we can evaluate it at s is equal to p1. And when we do that, all of these terms here will go to 0. So this is a review of just what we talked about at the end of class last time. And this part here will also cancel out, and we will get that this term is equal to C1. Okay, so we have that s minus p1 times our rational polynomial in s, f of s, evaluated at s is equal to p1 is equal to C1. So this gives us a procedure for finding each one of these coefficients, C1 through Cn. We simply go through, multiply by the root, so s minus p1, s minus p2, and so on up to s minus pn. And we can use this fact to find each one of these coefficients C1 through Cn. So what I wanted to start with today is to just show you a quick example. And we're just going to look at a numerical example to make this clear. You will be using this procedure in the homework. So let's start with just this arbitrary example of, let's say we have some solution, some particular solution to an LTI system. Y of s is equal to, we can factor it into s plus 2, s plus 6 over s times s plus 1, s plus 3. Okay, and we know from partial fractional expansion that this system can be written in terms of a linear combination of its poles. So we can write this as C1 over S plus C2 over S plus 1 plus C3 over S plus 3. So note that these three terms here, these are just the roots of the denominator. Okay, so what is our first step here? Let's say we want to find C1. What do we do? Right, so we multiply the entire, both sides by S. And if we do that, this S in the denominator here will divide out. And we will end up with S plus 2, S plus 6, S plus 1, S plus 3 is equal to C1 plus C2 S over S plus 1 plus C3s over s plus 3. Okay, now what do we do? Close. We put, what's the value of the,
Zero.
what's the value of our root here?
Zero.
0. Yeah. Okay, very good. So we evaluate this expression at s equal to 0. And we will get, this here will become 2. This here will become 6. This here will become 1. This here will become 3. This here will become 0, right? And this here will become 0. And if you multiply all of these out, you will get that C1 is equal to 4. All right. All right, so let's go ahead and do this for the second root of the denominator here. We end up with s plus 2, s plus 6, s times s plus 3, evaluated at s is equal to -1, is equal to, and we can just skip this step here. We know these other terms will go to 0, and so we will end up with just C2 on the right-hand side. And if we plug in s is equal to -1, what we will end up with is that C2 is equal to -2.5. I'm not going to carry out the full arithmetic there, but you will end up with that value. Okay, and I'm going to start a new page here in a second, but I will give you a second to write that down. All right, and our final root is -3. So we're going to multiply it through by s plus 3 on both sides. And we will end up with s plus 2 times s plus 6 over s times s plus 1, evaluated at s equal to -3 is equal to C3. And from this, we get, if we evaluate this, we get C3 is equal to -0.5. All right, so now what do we do? So we're trying to take y of s and put it in the time domain. So what do we first need to do here? Right, so we will take the inverse Laplace transform. Very good. So first, let's just go ahead and plug in these values for C1, C2, and C3. So we will end up with y of s in the frequency domain is equal to 4 over s. That's that first term with C1 minus 2.5 over s plus 1 minus 0.5 over s plus 3. Okay, so let's go through for each of these terms and find what each of these are in the time domain. Let's take the inverse Laplace transform. We'll end up on the bottom here with yt. Okay, so let's take a look at this first term here. We have 4 over s. What does this become in the time domain? Right. And what is u of t again? Right. So this is distinct from the ut we've been using. So we've been using the variable ut to represent any input. Here in this table, it means 1 everywhere greater than 0. 1 where time is greater than 0. So this is the step function. So I'm going to write that as 4 times 1t. So this is the notation I'm going to use for the step function, just to keep it distinct from u, which we've used for a different purpose so far. Okay, so 4 over s becomes 4 times 1 of t. What does the second term here become? Yeah, it'll become exponential here, so we'll end up with 2.5 times e to the negative t, right? And then here, just following the same pattern, we will get minus 0.5 e to the negative 3t. Okay, and that's how you can perform partial fractional expansion to solve the inverse Laplace transform. Okay, and that is our response in the time domain for our function in the frequency domain. Cool. Are there any questions on this process before I move on? All right. Is this something that was covered in undergrad differential equations? Yes. Anyone hasn't seen this so far? You haven't seen this so far? Okay. So partial fractional expansion, it's often taught in undergraduate differential equations, but it's just a general mathematical fact that you can take a rational polynomial and break it down into separate terms like this. So it's a useful technique, particularly for this type of problem. Okay, so what I'm going to do now is I'm going to move back to our motivating example. So I started off this whole discussion about partial fractional expansion because we were attempting to find the response of our RC circuit, our power grid system with the storage element. We were attempting to find the response to a step input. And we found that we ended up with a term that it was difficult to take the inverse Laplace transform of naively. So we're going to go back to that example, and we're going to take a look at how we can use partial fractional expansion to solve it. Okay, so we have our power grid system. We're treating it like an RC circuit. So it's a power grid with some resistance, some storage element that we're representing as a capacitor. We have a constant step input to the system of 100 volts. So I'm just going to call this V. V being a constant equal to 100 volts, where time is greater than 0. Our resistance is equal to 1 mega ohm, and our capacitance is equal to 0.2 microfarads. All right. So we have that our input to the system, as I just wrote over there, is equal to 100 volts, which I'm just going to call V. We have that our initial voltage, we're going to look at the system with some initial conditions. So we have that the initial voltage in the capacitor at time 0 is equal to 5 volts. Okay, and we're going to try to find the particular solution to this power grid system for a step voltage input. Okay, so our input to the system is the step voltage input. Our output that we're interested in is the voltage at the capacitor. And when we're looking at the system like so, we have that the dynamics of the system are described by the following ordinary differential equation. So the dynamics are given by Vc dot of t is equal to, Vc dot of t. If we monetize it, we get Vc dot of t plus 1 over Rc times Vc of t, capacitor voltage, is equal to 1 over Rc times V of t, our voltage input. So let's go ahead and let's take the Laplace transform of this entire differential equation here. What do we get when we take the Laplace transform of the first derivative of the capacitor voltage? S times, right, so we'll get S times Vc of S. Is there something else we need to consider? right, minus the initial conditions, which is VC times 0. So note that this is capital V here, this is little v, so this is the initial condition in the time domain. This VC of S is in the frequency domain, it's different. Okay. What about this second term here? If we just have VC of t times 1 over RC, just VC of S. Okay, very good. It's been a while, so I'm just quizzing you. It's 1 over RC times VC of S is equal to, okay, now what does this here become? Let's call this, instead of V of t, we'll just call it V because it's a constant. What does this become? Yes, so this will become 1 over RC times V over S. And note that this V here, this just means 100 volts. Yeah, so if you have a constant starting at time 0, that will become 1 over S in the frequency domain. Let me make a note here. This is 100 volts times the step function, right? It's important that it starts at time 0 when we're using the unilateral Laplace transform. Okay, so now what we can do is we can take this expression, we can factor out VC of S. So let's go and do that. So if we factor out VC of S, we get S plus 1 over RC, quantity all times VC of S, is equal to V over RC times 1 over S plus our initial conditions VC times 0. All right. And let's go ahead and divide through by this term here. So we'll end up with VC of S is equal to V over RC, all divided by S times S plus 1 over RC, plus the term corresponding to our initial conditions, VC at time 0, divided by S plus 1 over RC. Okay, so this was the problem we ran into initially. We didn't know how to take the inverse Laplace transform of this term, right? We're going to need to use partial fractional expansion to solve for this term. This term here, we could easily take the inverse Laplace transform of just by looking it up in the table. This corresponds to our exponential term, our exponential decay. Okay, so let's just perform partial fractional expansion on the first term. So I'm going to say doing PFE on the first term. We have that V over RC all divided by S times S plus 1 over RC is equal to what will go on the right-hand side here if we're breaking it into its, so we can do C1 over S plus C2 over S plus 1 over RC. Very good. Okay, so let's go ahead and do PFE. Let's multiply through by S. I'm going to start on a new page here really quick, but I'll just let you finish writing. So the game plan here, we're going to multiply through by S, evaluate at S is equal to 0. That'll give us C1. And we're going to multiply through by S plus 1 over RC, evaluate it at negative 1 over RC. And from that, we'll get C2. All right. So let's go ahead and do that. Okay, so C1 we know is equal to, if we multiply through by S, we will get on the left-hand side V over RC divided by S plus 1 over RC, evaluated at S is equal to 0. If we do this, we'll get V over RC divided by 1 over RC, which will give us simply what? Yeah, it'll just give us back V. Okay, 100 volts. And for C2, we have that V over RC divided by S, evaluated at S equal to -1 over RC, will give us V over RC divided by -1 over RC. That's just going to give us back -V. Okay, so if we go back and we plug in these coefficients C1 and C2, we have that VC of S is equal to V over S. So I'm just going back here. I'm plugging in C1 and C2, and I'm going to add on this third term corresponding to the initial conditions. So we have that VC of S is equal to V over S minus V over S plus 1 over RC, plus our third term corresponding to the initial conditions, VC of 0 divided by S plus 1 over RC. All right, cool. So let's take the inverse Laplace transform and let's see if you can do it from memory here. What'll this term here become? V over S. Right, it'll just become V. Yeah, V. I'll just write V times step function. This here will become, yeah, the exponential term, so VE to the -1 over RCT. And this term here will also become another exponential term. This will become VC times 0 times E up E to the -1 over RCT. So very good. This is the inverse Laplace transform here. And this is our response in the time domain, VC of t. We can simplify this a bit, and I will do so here. We have that VC of t is equal to V plus quantity VC at time 0 minus V all times E to the -1 over RCT. And if we plug in our known values for V and VC of 0, this becomes the same answer we got before, 100 minus 95 times E to the -5t. So that's how you can use PFE to solve for the response in the time domain. Well, are there any questions on that procedure? Any questions, right? So again, in today's lecture, I wanted to make sure you have all the material you need for the homework. So I really want to make sure that these examples are clear. Okay, so if there's any questions, please let me know. Okay, I have a little quiz question for you then. What is the transfer function of this system? I'll give you a minute to think about it, because this is an important concept, and I know it's tripped up several students in the past. So can any of you tell me what is the transfer function of this power grid system? I'll give you a minute to think about it. And I'm looking for the actual, the function, the expression. So does anyone want to volunteer? What is the transfer function of the system? Does anyone have a guess? I believe we actually derived this in the previous class. What's the transfer function of this power grid system?
1 over plus 1 over half. I'm sorry, 1 over 2. Or is it also have the factor one over x?
So let's go back to this equation here. So how can we find the transfer function of a general LTI system?
It's the characteristic, or you do the characteristic.
Right. So you can also find it by evaluating the system with what type of input. Yeah, an impulse input. So let's say we have our system v dot c of t is plus 1 over RC. Vc of t is equal to 1 over RC times u of t. If we let this u of t be the Dirac delta, and we take the Laplace transform, this gives us our impulse response. So in general, when you are looking at the transfer function of the system, you ignore the initial conditions and you just look at what would the response be to an impulsive input, assuming no initial conditions. Okay, so this would become S times VC of S plus 1 over RC V of S, VC of S is equal to, what does this last term become? Just 1 over RC. Okay, and so your transfer function, if we factor out VC of S, S plus 1 over RC, it's equal to 1 over RC. Your transfer function will become, yeah, so you'll get that, VC of S is equal to 1 over RC over S plus 1 over RC. Note that I probably wrote this in a way that I should not have here. The transfer function is when you're trying to go from some input U of t to some output. So actually we would write here, this is just some generic input U of t. When we take the Laplace transform, we get 1 over RC times U of S. And then our transfer function is actually VC of S over U of S is equal to H of S. But it's equivalent to finding the response of the system when the response is a unit impulse. So if U of t is equal to the Dirac delta, then H of S is equal to VC of S. Okay. So this is something that's tripped up students in the past. When we're talking about the transfer function, we're really just talking about the function that takes us from some input to some output. You don't use the initial conditions when you're computing the transfer function. And in fact, you can think of the initial conditions as corresponding to impulsive inputs, right? So if we go back, so this here is our transfer function, 1 over RC over S plus 1 over RC. If we go back, we see that our expression for VC of S, right? We could factor this in terms of our transfer function. So we have that. Let me just erase this here. Can factor this in terms of our transfer function. So we have VC of S is equal to V over RC over S times S plus 1 over RC plus VC of 0 over S plus 1 over RC. So we can factor out H of S. From this expression, we get that VC of S is equal to our transfer function H of S, which is 1 over RC over S plus 1 over RC, all times V over S plus RC times VC0. Is that right? I believe that's correct. Yes. So you can think of, if we treat, if this is our transfer function, H of S, you can think of this as being our overall input, U of S, which includes both the step input as well as the input corresponding to our initial conditions. Okay. So just when you're using transfer functions, please be aware that it's the function that takes us from our input to our output. When you're computing the transfer function, you don't account for the initial conditions. Okay. Are there any questions on that concept? Great. Okay, so with that, I'm going to, again, slow things down, and I'm going to go through the case of repeated roots. So this, again, will help you for your homework. We're going to look at the case of repeated roots. And this is, again, talking about partial fractional expansion. So repeated roots always kind of mess things up. We're going to see this later on in the class too, where it's going to make things more difficult for us. But when we have repeated roots in our differential equation, or repeated roots in our characteristic equation, we need to use a slightly different procedure to find the solution. Okay. So let's say we have some function f of s. This is a rational polynomial. It can be factored as before with its denominator roots on the bottom, and we're going to factor it into its partial fractional expansion form. So for the case of a system with repeated roots, we end up with something like C1 over S minus PR. So PR corresponds to the root that is repeated. So we have C1 over S minus PR plus C2 over S minus PR squared. So when we have a root that's repeated in the partial fractional expansion, we'll end up with that root being raised to its higher powers in the denominator, all the way to CR over S minus PR to the rth power. So this root is repeated. So the root is repeated r times. Okay, and then we may have other terms as well. So we have other roots all the way up to CL over S minus PL. Okay, so this is the same partial fractional expansion as before, except we now have some root that is repeated. And in this case, it's repeated R as in Romeo times. Okay, so the solution procedure for this case is very similar. We start by multiplying through the highest power of this root in the denominator. So we start with the highest power and multiply it through. And we end up with S minus PR to the rth power times f of s, evaluated at s equal to PR is equal to CR. Okay. And you can see this in the same way as before. If we multiply through by s minus PR to the rth power, all of the other terms except for this one go to 0 when we evaluate at s equal to PR. So we start with the highest power. That gives us CR. But unfortunately, for the rest of these roots, we need a different way of finding them. For the rest of these repeated roots, we need a different way of finding them. So what we can do is for the next root, for the next coefficient, so this would be this would be CR minus 1. Okay, we start with the previous expression. Okay, so we start with S minus PR to the rth power times f of s is equal to C1 times S minus PR to the R minus 1th power plus C2 S minus PR to the R minus 2th power, and so on, all the way to CR minus 1 times S minus PR plus CR plus dot 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 all the way to all of the other roots that are not repeated. So we take this and note that if we evaluated this at S is equal to PR, we would be able to recover CR, right? But for recovering all of these other coefficients, CR minus 1 through C1, we need to do something slightly different. So what we can do is we can take this expression and differentiate both sides with respect to S. Okay, so we're going to take this expression, we're going to differentiate both sides with respect to S. Okay. And let's see what's going to happen here. So what we will end up with is what's going to happen to this root or this term here. So what happens if we take this term here and we differentiate it? Right. So, right, we can, yeah, so that's exactly right. So if, for instance, if we apply the chain rule, let's let this be U or something. If we have, this is just an aside, d by ds of C1 times U to the R minus 1. Okay, this is equal to d of C1 U to the R minus 1 over du times du by ds. Sorry, this is this here is not correct. This should be C1 of S minus PR to the R minus 1, where this here is U. And if we do this, what we will end up with is this becomes C1 R minus 1 U to the R minus 2 times 1 minus 0. Okay, and that will give us simply R minus 1 times C1 S minus PR to the R minus 2th power. Okay, so if we differentiate both sides, what will happen is that we will end up with d by ds of S minus PR to the rth power times f of s is equal to, as we showed before, R minus 1 C1 times S minus PR to the R minus 2th power plus r minus 2 times C2 to the S minus PR to the r minus 3rd power, and so on, all the way till we get to C r minus 1. Okay. What happens when we differentiate this term with respect to S? This goes to 0. Okay. And so what we'll have is all of the rest of the terms will end up being 0. And then if we take this and we evaluate it as before at S is equal to PR, we can recover CR minus 1. Okay, because this term here will go to 0. This term here will go to 0. All the other roots will go to 0. Okay, so we end up with d by ds of S minus PR to the rth power f of S evaluated at S equal to PR is equal to C r minus 1. And we can apply this in sequence to find the other coefficients C1 through CR minus 2 just by taking the higher order derivatives each time. Okay, so this will generalize for the higher order derivatives. All right. So yes.
So when we're doing this on the homework, and we need to like differentiate this subtended term,
Mhm.
would be averse to us putting in the MATLAB something or we do it by hand?
It shouldn't be too difficult. So we're not going to go any higher order than just 1 for the homework. So shouldn't be too difficult. Let me go through just a quick example. I'm going to probably run out of time today, but I'm going to go through a quick example here. Let's say we have a function f of s is equal to 1 over s squared times s minus 1. So we have a repeated root where s is equal to 0. Okay, and we know that we can factor this into C1 over S minus 1 plus C2 over S plus C3 over S squared, right? So let's go ahead and start with the easy root. So let's find C1 first. We know that if we multiply through by S minus 1, we get that C1 is equal to S minus 1 times, 1 over S squared. So it will end up with C1 is equal to S minus 1 over S squared evaluated at S equal to -1. Okay, and sorry, the S minus 1 in the numerator shouldn't, it goes away. So we'll get 1 over S squared. And this will just become 1. We evaluate it at S equal to -1. Okay, for C2, what do we do first? When we're looking at repeated roots. Actually, let's look at C3 first, right? So we start with the highest power on the root, we multiply through. So we get 1 over S minus 1 evaluated at S equal to 0. And that's going to give us -1, right? All right, so now we can find C2. This is the tricky one. So again, we've multiplied through by S squared. We're going to need to take the derivative of 1 over S minus 1 with respect to S and evaluate this at S equal to 0. If you take the derivative of this and apply the chain rule, I'm kind of running out of time, so I'm just going to write it out. You will get -1 over quantity S minus 1 squared. And if you evaluate this at S equal to 0, you will get -1, exactly. Okay, so your answer will be f of S is equal to 1 over S minus 1 minus 1 over S squared minus 1 over S. Okay, so really quick, what happens when we take the inverse Laplace transform? So this one we know becomes an exponential term, right? Let's take the inverse Laplace transform. We have f of t is equal to, this becomes e to the t, right? Okay, we take the inverse Laplace transform. We know what this is. This just becomes step function, right? So it's -1. I'll call it 1 of t. What does this one turn into? Yeah, exactly. So if we go back to our Laplace transform table, we have that if we have 1 over s squared, it becomes t. Okay, so it's a term that is dependent on time. It's a linear function of time. Note that this is a generalization of this term here, right? So if we have our coefficient and the exponential equal to 0, we'll get the same thing, right? And this is going to have important implications on Thursday's class for stability. Okay, we're going to have to worry about what repeated roots might do for the stability of our system. Okay, and we'll talk a bit more about it on Thursday. Okay, are there any questions on this procedure before I move on? So this is something you will need for your homework, and I wanted to make sure you had the basic procedure in place. Okay. Any questions on repeated roots? These ones are kind of annoying to deal with, but they do have important implications, as I noted. In particular, yeah, when we're talking about the stability of the system, you have to be careful. Okay. Right. Oh, by the way, when I say the stability of the system, what do you think I mean by why would repeated roots have an issue with the stability? Why would repeated roots cause an issue for stability? I guess I haven't defined stability yet, but why might it have a problem? So why might it be a problem that you have this t term here?
Like if everything else is like decays or periodic, if you also add like a linear component, it's not going to be the same over time.
Right. So we'll talk about what the definition of stability is for the purposes of this class. But if you have any term with a repeated root, so if you have any term with a repeated root, you'll end up with a term that can potentially grow over time, right? So your system will not decay to some steady state. It won't decay to 0. If you have repeated roots, you will end up with some component of the system that just grows indefinitely over time in some cases. Okay, and we'll talk about what conditions that occurs under. Okay.
If the e to the t would make it like more unstable.
Yeah, so in this case, it doesn't really matter because of this e of t term. But if we had all the other terms being stable, this term would cause a problem. Okay, how much time do we have? I don't have my phone on here. 10 minutes. Okay, so what I'm going to do is I'm going to just quickly go through an example of a system with higher order dynamics and how you can solve something like that via inverse Laplace transform. I probably won't have time for the entire example, but we're going to go through the example of the structural system again and how we can solve that using the inverse Laplace transform technique. Specifically, how can we make it amenable to the inverse Laplace transform technique? So we have our old friend, the structure, okay, has some mass m and has stiffness and damping, and it's being induced with some displacement. So we're going to look at just the homogeneous case right now. Laplace transform will still help us here. So let's look at the homogeneous case. We have that our equations of motion are given by mx double dot plus cx dot plus kx is equal to 0 for the homogeneous case because there's no force input. And we showed last time that we can write the system by monetizing it as x double dot plus 2 zeta omega n times x dot plus omega n squared x is equal to 0, where omega n is our natural frequency and our zeta is the damping ratio. And we defined those terms last time. Okay, so let's take this system here and apply the Laplace transform to it. Okay, so let's take this, apply the Laplace transform. And this is the homogeneous case, so we do have to care about the initial conditions here. So what do we end up with when we apply the Laplace transform? What happens to this first term? Becomes s squared x of s minus, and I'll just give, yeah, so for the initial conditions, we have s times x naught, our initial displacement, minus x dot at time 0. So that's the initial velocity. Okay, so you know the drill. For the next term, we will end up with 2 zeta omega n times s xs, exactly. And we also have to account for the initial conditions on this term as well. So let me just group these to make it clear what I'm doing here. So we will have minus 2 zeta omega n times our initial displacement x at time 0. Okay, and our final term here is just going to be the natural frequency squared times x of s equal to 0. Well, I'll just group that one too. Okay. All right, so we can factor out x of s. Can factor out x of s, and we have x of s times quantity s squared plus 2 times the damping ratio times the natural frequency times s plus natural frequency squared is equal to, and on the right side, we'll have all of the terms corresponding to our initial conditions. So we'll have s times x at time 0 plus x dot at time 0 plus 2 times the damping ratio times the natural frequency times initial displacement. And I'm running out of space, but I got it. Good. Okay, and we can write out our expression for the displacement in the frequency domain simply by dividing through by this term on the left-hand side. So dividing through by our characteristic equation, we'll end up with s times x at time 0 plus quantity x dot at time 0 plus 2 times the damping ratio times the natural frequency times the initial displacement all over our characteristic polynomial s squared plus 2 zeta omega n s plus omega n squared. Sorry, I'm going a little fast, but running out of time today, and I might pick this back up next time. So this is our expression for the dynamics of the structure in the frequency domain. How can we take this and convert it to the time domain? So this is a form we haven't really seen yet. Is there anything in our Laplace transform table that looks like this? So these ones kind of look like it, right? But it's not quite in the exact form we're looking for. So what we can do is we can use a technique from what you may have learned in high school or middle school called completing the square. Does anyone remember completing the square? I feel like this class is like a great review of middle school and high school algebra. Yeah, so if you ever asked, what am I ever going to use this for? Here you go. We can use a technique called completing the square to write the system in the form that we want. I have to figure out how to work conic sections into this class at some point. If we have a system of the form ax squared plus bx plus c is equal to 0, if we let d be some variable equal to b over 2a, if we let e be some variable equal to c minus b squared over 4a, then we can rewrite this expression as a times x plus d all squared plus e is equal to 0. Okay, and that's going to give us an expression that is equivalent to what we see in the Laplace transform table here. So let's go ahead and do that. I know we're running out of time. I'm just going to go by that clock up there because I have my phone off. But for this case, we have d is equal to zeta omega n. And we have that E is equal to omega n squared times 1 minus the damping ratio squared. Okay, and so we have that our initial expression for the characteristic equation or a characteristic polynomial s squared plus 2 zeta omega n s plus omega n squared is equal to 0, that this corresponds to s plus zeta times the natural frequency all squared plus omega n squared 1 minus zeta squared is equal to 0. And we can take this here. We have another expression that we previously defined for this. If we define omega d as being equal to omega n times the square root of 1 minus zeta squared, this here becomes omega d squared. All right. And so what we end up with is x of s we can now write as follows. We have our numerator, same as before, s times x at times 0, plus quantity x dot at times 0, plus 2 times zeta times omega n times x at times 0 all over. And now we have our new denominator, s plus zeta times the natural frequency all squared plus omega d squared, right? So now we have that the denominator corresponds to these two denominators here. So all we need to do is we need to rearrange the numerators so we can separate out this numerator to put it in these forms. And from there, we can take the inverse Laplace transform to find the response. I'm out of time, so I can't do it today. We'll pick this back up on Thursday. But I hope you have a great rest of your week, and I will see you back in 2 days.